So I am Lipman. I'm working at Redis. I've been working there for the past 7 years almost. Today I am the tech lead behind RedisGraph, which is a property graph database built on top of Graph Plus. I'm going to focus specifically on use cases where we have constantly changing graphs, what maybe I would refer to here as dynamic graphs. So I should mention that as in Scott's talk, there is a clear mapping between graphs and sparse matrices. And so RedisGraph uses sparse matrices for both its underlying graph representation, but it also uses sparse matrices and linear algebra to perform all kinds of different graph operations, such as graph traversal. So I've been a big believer in GraphLess. I see a very bright future for it. And this is maybe a glimpse into it. And so with the dynamic graphs, you can think about applications that are constantly hitting the server with requests to modify the underlying graph topology. Add edges, delete edges, add new nodes, delete nodes, and this goes on all the time. So whenever, for example, an edge is added, we need to go to the corresponding matrix and make the proper modification to reflect the graph topology. So here a new edge had been added, and so we need to go to the proper matrix and make that modification. Now, this might seem like a trivial operation. It is a common operation. We perform it over and over again, but in terms of performance, it might be a bit problematic, specifically in the worst case scenario, which is a use case where we have a one-to-one read-to-write ratio, meaning make a modification, read something from the graph, make another modification to the topology, then reread the topology. So the matrices themselves are unable to perform the modification in a lazy manner. They cannot accumulate this set of changes and say, okay, I'm going to wait with this set of changes up until the point where I actually need to see those. In these cases, we're flushing the matrices constantly. And as we will see, this is a really expensive operation to perform. Some numbers. So I ran a quick benchmarking different graph sizes or matrices dimension with a different set of number of active entries, which corresponds to the number of edges. And you can see the average update time, which is not great. Starting with small matrices, small graphs, and then building up. So this basically kills the idea. I mean, from my perspective, if you're dealing with constantly changing graph, this basically kills the entire idea. And so maybe we should try and understand, if we want to resolve this, we should maybe try and understand why are we getting those numbers. And this, you will have to excuse me, but this goes into a little bit of a technical detail regarding the underlying matrix, sparse matrix representation. And so we're using CSR as our main format for most of our matrices. And in CSR matrix representation, we're dealing with a hierarchy of 3 arrays. There is the top array of length n plus 1. We have 1 entry for every row in the matrix. And then we have 2 additional arrays. One we refer to as the columns array, and another one the values array. And these are of length n vals. N vals meaning the number of active entries in the matrix. And so the first array is an offset into both the columns and the values array. So what would happen to those arrays whenever we're adding a new entry in the matrix? Well, first off, we need to update the offsets, right? And we have actually added the worst, in terms of positions, we have modified the 00 entry, which in this case is the worst entry to modify. So the offsets needs to be shifted. So there's a lot of additions now going on in this array. The other two array, those are going to be reallocated, which is another expensive operation. Then we need to figure out where is this new column falls in. We put the column number in the right entry, and all of the entries that follows, those are going to be shifted. Again, it's an expensive operation. Similar thing goes to the values array. There is one nice optimization that had been done by Tim Davis here. And in case we're dealing, for example, with a Boolean matrix, where all of the values in the matrix have the same value, for example, true, there's no need to maintain this third array. We can just drop it. What's the value in entry ij? It's all the same, so there's no need to maintain this array. And I think that the biggest problem here is the fact that the cost of the change grows as you're dealing with bigger and bigger matrices. And this is a property that you don't want in a real-time or a near real-time database system. So we're dealing with a common operation to perform. We know it is expensive, but the worst thing is that it gets more and more expensive as your matrix or your graph are getting bigger and bigger. So how did we try to tackle this challenge? There are a number of ways, maybe. There's a paper called Vertical, Temporal, and Horizontal Scale of Hierarchical Hypersparse Gauss Matrices. Unfortunately, this idea does not apply here. This paper talks about the situation where you're dealing with a stream of additions or setting to the matrix. So you try to accumulate those in small matrices, and then you pouring those changes onto bigger matrices. And when you want to see or you want to work with your entire gut, you need to collapse those. And so this doesn't work for us in the read-write one-to-one use case. Another idea which we've tried is to switch to a block representation of our matrices. So basically A, B, C, and D here are block matrices, something similar to this. So this had a nice potential because every change is local to a specific block, and maybe we can control the size of these blocks, keep them small. But then other operations such as matrix-matrix addition or matrix-matrix multiplication, these get a little bit complex and expensive in time of runtime. And so what we ended up using is a concept that we refer to as delta matrices. And the idea behind a delta matrix is to break down or represent this matrix as a set of three matrices. The first one we refer to as M. It's basically the original A. And then we have two additional matrices, dp, which is delta plus, and delta minus. The important thing about M is that it is immutable, because we know that the problem is changing this big matrix. We don't want to touch it, and as such, it is immutable. Delta plus captures the recent additions, and one thing to note here is that it is not a classic CSR matrix, but we're using a different format here, which is hypersparse. I'm not going to go into the details, but it is there's an additional array in the three-array hierarchy representation. Delta minus captures the recent deletions. It is also hypersparse. And what happens when we want to add a new edge, for example, at the 00 entry, we simply set that in delta plus. And this is a cheap operation to perform because there are not too many entries in the matrix, and the format is a little bit cheaper to deal with. Now, if I wanted to delete it, I can simply modify delta plus. Now, what happens if I want to delete an entry from M? I just mark the deleted entry in delta minus, and what if I want to re-add it back? I just remove it from delta minus. And so I cannot continue on accumulating deltas infinitely because I would be back at the same spot that I was at the very beginning. And so what we've done is to basically set a threshold that says whenever the amount of changes that I've accumulated is greater than this threshold, then I'm going to need to flush those changes into M. And how are we flushing? The new M is equals to the previous one masked by the complemented delta minus plus delta plus. And it looks something like this, assuming these are our underlying matrices. Let's start with the complementation of delta M, basically reversing active and non-active entries, masking, removing those that were marked for deletion, and then adding the recent deletions, and we're ending up with the new M results. So the column to look at is the third and maybe the fourth column. And what's important to see here is that not only that the update time are pretty reasonable, I would say, the important thing to take here is that they're pretty much constant or not affected by the size of the graph or the matrix that we're working with. And you can see the scale or the improvement factor on the fourth column. Just viewing this visually, these are the updates made on the delta matrix, pretty constant, are not affected by the graph size. And this is CSR sparse using the sweet sparse implementation, which just, we could not work with this as it is. So getting to the end of it, a few links which I found to be interesting or worthwhile. The Graph Plus documentation, LDBC, which already had been discussed, and if you want to, the benchmark that I have conducted is available on GitHub. Maybe a little bit on future work. So we're still interested in block matrices. I think there is great potential behind those, especially when we try to distribute the graph. The idea is to distribute the different blocks on different nodes, and then still all of the linear operation can still be performed. So that's one thing we want to revisit. The other thing that we find to be interesting is MVCC, so version multi-currency control. So basically, we want the delta matrices to be versioned. So maybe changing the concurrency module of RedisGraph. And with that, I wanted to thank you.
Thank you. I have a question right away. How do you deal with node inserts and node deletes in this model?
Yeah, good question. So node insertion, basically, let me go back to some matrix. Let's go all the way back. Yes. So the matrices that we are managing within RedisGraph are all square matrices, and by n. Usually, we leave enough space to accommodate new nodes. Eventually, we will run out of space, in which case we're going to have to resize our matrices because every node is corresponding to a given row or a given column. So eventually, we would run out of space and it will be a resize. In terms of deletions, at the moment, matrices do not shrink. And so the next time in which you introduce a new node, we would just reuse the deleted ID. Right.
So you were talking about a threshold in which to essentially control the batching, right? Did the threshold stay the same for all of the different graph sizes, or did you adjust that threshold based on the graph size? That's my question.
Yeah, that's a good question. At the moment, the threshold is configurable, so the user can play with it, see what works best for them. We're not trying to be sophisticated about it. There's a reasonable default, which we found out to be working fine. But if our users, find themselves in a situation where they want to tinker with it, then it's a runtime configuration where they can adjust the threshold. But it would be interesting to really find a good correlation between a matrix dimension and the density of a matrix and the right threshold. Yeah.